Hello, yo, welcome to lesson 53 of my DP chemistry curriculum. Today we're going over structure 2.2.15, sigma bonds formed by the head-on combination of atomic orbitals where electron density is concentrated along the bond axis. We'll explain that, as well as pi bonds formed by the lateral combination of p orbitals where electron density is concentrated on opposite sides of the bond axis. And we'll be explaining that. So this whole section basically goes to answer the question, what happens to orbitals during a covalent bond? So we know electrons are shared, but how does this actually happen? So to answer this, we're going to start off with sigma bonds. We use the symbol sigma, lowercase, to represent this. And to do that, we're going to start with the simplest covalent bond and the simplest sigma bond, hydrogen. So when we take one hydrogen atom plus another hydrogen atom, which we can represent their 1s orbital as such. We've done this representation before. When we bring them together, we get hydrogen, which is represented by H2 as it's a diatomic element. Their s orbitals, which keep in mind are spherical, overlap. So this is spherical, and this is what we call SS overlap. So we have this overlap of the orbitals where we can notice that the electron density is concentrated in that section. So this is our formation of a covalent bond, a simple single covalent bond. This is also what we would call a sigma bond. This is where there is a head-on overlap, overlap, and and electron density is concentrated on what we call the bond axis. So what do I mean by bond axis specifically? Well, in addition to being the bond axis, this is also the nuclear axis, and I'll discuss that as well. Nuclear axis. Oh, let's try that one again. Axis. And what that means is if we look at the nuclei, meaning the one proton in each hydrogen atom, and we draw a line through the nuclei, we get this line, which actually, let's go ahead and represent this in a different color. This is what we would refer to as the bond axis. So it's where that covalent bond is happening. That overlap occurs directly smack dab in the middle of that axis. So this is our sigma bond. All right. Now, this doesn't necessarily have to happen with s orbitals. We have other types of overlaps. And so we also have a p-p overlap. And this is where we have two p orbitals. Oh, gosh, I have to do a lot of drawing today and will really notice my artistic skills starting to struggle. So the p orbitals have kind of moved out to concentrate their electron density closer to the overlap. And once again, our bond axis would be right down the middle. So I'll use that blue to represent the bond axis. So this is our PP overlap. We also have SP overlap. So you'll start to notice that we actually really need to understand the shape of these orbitals as we talk about sigma bonds, because the shape is going to dictate this overlap and where it actually occurs. So this is our SP overlap. Really important to constantly keep in mind is that the area of overlap is where electrons are likely to occur or to exist. Because electrons are always moving around, this is just the region that they're most likely to exist in that overlapping area. The density or the size of the orbital actually is a reference to the electron density. So we have greater electron density here with the most in that overlap section. Last thing we need to note is that sigma bonds are always found in single bonds. Or you know what? Let me reverse that. Single bonds are always sigma bonds. Are always sigma bonds. So every time you see a single bond, that is going to be a single bond. It's an overlap on the bond axis of either S and S, S and P, or P and P orbitals. All right, so let's move over to pi bonds. These are where we start looking at things in a little more of a three-dimensional way. So we use the symbol pi to represent pi bonds. And I don't think that's very surprising. And pi bonds are specific when forming double or triple bonds. So we form pi bonds to make the double and triple bond. And what happens here is that the electron overlap happens off the bond axis. And we'll see why, and it's due to the shape of the bond. Off the bond axis, off the sigma bond. And the reason this occurs is because our electron pairs strongly repel, as well as it's due to the repulsion of the electron pairs as well as the shape of the orbitals. However, the shape of the orbitals are affected by the repulsion of the electron pairs, so it's a little one-to-one on that. So due to this and due to how they're going to form, we only use p orbitals in pi bonds. So let's see what actually happens. To get this straightforward, we're going to use our 3D plane. So bear with me a moment as we make our three-dimensional plane. And we've got our X, our Y, and our Z axis. I'm going to do a little bit of cheating and just duplicate this 3 times. But we're going to be looking at our X, Y, and Z orbitals. So here's our X orbital, our Y orbital, and our Z orbital. Remember, this is px, py, pz. All right. So we already know that p orbitals can form sigma bonds by these head-on collisions. So maybe we have a px orbital here, and we have, you know what, let's do a second p orbital. As these move together, we'll get some overlap. So we'll see that, and we get this overlap right here. And this would be our sigma bond. The beautiful thing about sigma bonds is they're not really locked in place. This whole thing can rotate and flip around because it's just on one axis. Imagine if you had a sheet of paper and a separate sheet of paper, and you put a pen through both of them. You could rotate the papers around each other, but they'd still be kind of locked in place by that pen. You could not translate them left or right. That wouldn't work. So this is kind of what happens with a sigma bond. But we still have other orbitals that exist here. So we could have our 2 orbitals here now try and bond are PYs. So this would be our PX making that sigma bond. But the PY orbitals want to bond as well. And so PY would form our pi bonds. And the way this actually ends up looking is if we have our two bonds, this is one PY and one PY, and we add them vertically, or actually what we call laterally or lateral overlap, we get this new structure where they overlap. And so this would be lateral overlap or sideways overlap. And this is our pi bond. Now, you'll notice a couple things. Our bond axis is no longer, or our electron density is no longer in the bond axis. So electron density, or our overlap, is off the bond axis because our overlap is up here and down here. So it's above and below. So that's going to dictate a few things about this bond as well. Now, if we go back to our diagram of the paper, and I'm just going to go ahead and duplicate this, our pi bond is making that double and triple bond. So imagine now we have a second pencil through that same piece of paper, or those same two pieces of paper. We'll no longer be able to rotate the papers without tearing it or without the bonds twisting or getting weird and tangled. So pi bonds kind of lock the shape of the orbital or of the molecule. So before we move into examples and taking a more in-depth look on how these bonds actually interact or how the orbitals interact, we're just going to look at how we kind of quantify bonds. So if we have A and B, single bonded, double bonded, triple bonded, our single bond is going to be sigma, and so is our first bond in example 2 and 3. But our other bonds are going to be pi bonds. So our sigma will always be that first bond, with our pi bonds being the other one or two bonds. So this is going to help us answer some questions that the IB might ask you. So for example, identify the number of sigma and pi bonds. And they'll give you some complex molecule. So here is our complex molecule. We'll put our electron pairs, and we're going to add some double bonds here, double bond here. We'll double bond to an oxygen, and we'll double bond to an oxygen. So go ahead and pause the video, see if you can do this yourself. Then come back and we'll go over the answer right now. So for sigma bonds, every bond has one sigma bond. So all I have to do is count the total number of bonds, counting double as one as well. Something to note here actually is I missed a couple hydrogens. So if you are figuring this out or you're like, hey, I already noticed this doesn't work, that's why. So for our sigma bonds, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sigma bonds. All right, then for our pi bonds, all we have to do is count the double bonds or triple. 1, 2, 3. So we have 3 pi bonds, and that's it. That could be one full mark on your DP exam, and it's answered as easily as that. All right, so let's go over a little bit more of the nitty-gritty on how these bonds actually overlap and what it kind of looks like in a three-dimensional space on a two-dimensional page. So the thing we must always know is that sigma bonds must first be present before pi bonds. Always, always, always. So let's take a look at the compound ethene. It looks like this. You can probably quickly identify that there are 5 sigma bonds and 1 pi bond. But what do the orbitals actually start to look like when we form these bonds? So we have other ways to represent this. So I'm going to draw all our actual atoms first and then draw the orbitals. I'll use blue to represent our bonds, our orbitals. And you'll notice we have this overlap here. These join together. But the weird thing is with our p orbital, and I'm going to draw this as one big figure 8 shape. Oops, wanted to get that all in one. So we have this kind of attractive force here, and this kind of ethereal space is our 1 pi bond. So that is our pi bond right there. As we move into the next section, we'll talk about why we still have our p orbitals shaped like this, while these orbitals kind of have this weird funky shape that we haven't really covered. That's an orbital hybridization. But this is kind of what our representation of ethene looks like. However, this is still not the complete picture. When we form pi bonds, what actually happens is the p orbitals kind of stretch and change shape to overlap. Because again, an orbital is more just a region of space electrons are likely to appear. So by our current drawing, that means electrons will never appear in this space, only here, 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 and here, but not these. But we know that orbitals are specifically meant to describe where they could appear. So we can actually make this diagram even more detailed, which would represent, oops, I want to show the orbitals. So once again, I'll use this blue to represent the overlap, and we'll just start that one over. So we have that overlap there. We have these funky orbitals. But then what I mean by the p orbitals change shape to overlap is we get this weird kind of like almost curving of the orbitals. Now, with this, we are still making sure that we're not going through the bond axis. We still have our central bond axis right through the middle. That's where our sigma bond occurs. So bond axis. And this is happening above and below the axis. So we get these kind of weird shaped orbitals when they form this pi bond. Now, this is still only a double bond. So what happens when we form a triple bond? Well, we'll do that too with a different compound, ethyne. Oops. Ethyne is C triple bond C, single bond hydrogen on both sides. So what does this one actually look like? We'll try and do our best to do a three-dimensional drawing. So it's a linear molecule. And once again, we have our orbitals. And we have what formed our double bond before. So that formed our double bond. But when we actually look at this, this is going to be a little tough to draw, but we'll see if we can do it. So if you think about this as three-dimensional, we may have our overlap occurring on different planes. And so this is why it's kind of hard for students to often visualize this. This might be our P Z plane. If we say this is the z-axis, the x-axis, and the y-axis, that overlap may be on the PZ plane. Meanwhile, we get kind of this overlap above and behind and in front. And this red one, which is getting a little stuffy and hard to see, this red one is happening on the PX, and that's on our x-axis. So we kind of have this weird shape where if you were to look at it from the y-axis, so if the y-axis was coming straight for you, you have your bond axis, you have orbitals above and below, or I'll keep color consistent. We have our above and below, and then we have our side and side with our main one straight through the middle. And so it's very hard to kind of not comprehend, but it's very hard to visualize what this structure looks like from all angles. So this is something you'd want to try and build a three-dimensional model or look up some other videos that will have a three-dimensional model. But that is it for the shape and formation of sigma and pi bonds. The last thing we have to talk about is relative strength of bonds. And we can look at this through data, which is really nice because data is awesome. So we already know that single bonds are weaker than double, are weaker than triple. So usually this makes people think, well, sigma must be weaker than pi bonds. But this may not be true. We have to figure out how we can actually comprehend this. If we look at a single bond between carbon and carbon, the energy required to break that bond is 346 kilojoules per mole. That means that the energy required to break a sigma bond, sigma only, is 346 kilojoules per mole. Now, if we have a carbon double bond carbon, the energy required to break that is 614 kilojoules mole inverse. And this is a sigma bond and a pi bond. So what this actually tells me is that if we multiplied 346 by 2, we'll get something like 692. So times 2, we'll get like 692. 692 is far larger than our 614, which means that the pi bond does not add as much strength as sigma bond. It only added about 200, or sorry, it only added about 280, 270. We can do the math. So the real deal here, and what the key takeaway is that the pi bond is weaker. So the new question is, well, why is it weaker? And we can start looking at our actual shape to understand why it might be weaker than the sigma bond. If we look at the area of overlap, it is on the plane, the internuclear axis, it's on the bond axis. So our electrons in the sigma bond are much closer to the nuclei and therefore feel stronger attractive force. So our reasoning could be that sigma bonds have overlap, which once again represents electron density on the bond axis, the electrons are actually closer to the nuclei, or they have a stronger attraction. The other thing that we can do, or I should finish it, electrons are more strongly attracted to the nucleus or nuclei of both atoms. So we can also refer to it in terms of pi bonds. The pi bonds have electron density off the internuclear axis. We can literally see in our diagram that the nuclei of carbon are pulling in two separate spots off the internuclear axis, off the bond axis. That is going to be a much weaker pull than just one spot on the axis of the nuclei. That force is kind of being deflected almost, or being offset. So one of the really wonderful things that this tells us, and one of the larger pieces of evidence we have to pi bonds being weaker, is that we know that actually single bonds are less reactive than double/triple bonds. And that's more because those pi bonds are weaker and easier to break. The last thing we're going to go over is resonance, because we have to talk about pi bonds and resonance. And this is going to be very quick and very likely not going to be on a DP exam. But with pi bonds and resonance, what we really just see is that the p orbitals overlap together, which is a really odd way of saying it, but we can think about benzene. But first, we'll just talk about ozone because that's always my favorite for resonance. If we look at our structure for ozone, and I'm just going to be drawing skeletal structures, and we have resonance, we know that the single bonds or the double bonds can switch between here and here. And so we can kind of show that with the p orbital attraction. And so just the main idea that you actually need to keep track of is that the attractive forces or the resonant orbitals, gosh, this drawing is getting worse and worse as this video goes on. So this area of that double bond also can be represented with resonance via the same type of imagery. And that's because those p orbitals are going to have kind of that shared overlap. The picture I wanted to show you right before the end is that we can really see this in benzene, where we notice that the upper orbitals all kind of end up overlapping together to form this ring, and the lower, or it's not the upper orbitals, the upper portion of the p orbitals form a ring, and the lower section of the p orbitals also form a ring where they overlap to become kind of these donut-shaped electron clouds or orbitals of high electron density. So I hope this helps you understand sigma and pi bonds a little bit better. It gives you the confidence to use them on your DP exam, and have a great